Welcome to the webinar, introducing our new Coreform IGA structural simulation solver. So I'm your host, Matt Cederberg. I'm the CEO and co-founder of Coreform LLC. And this webinar will be presented by Greg Vernon, the Director of Product Management at Coreform, and Dr. Michael Scott, who is the co-founder and senior advisor at Coreform. So this webinar is being recorded and posted on YouTube after the event. So please ask questions through the QA panel throughout the webinar, and we will either answer you back through the back channel, or we will pause at an appropriate time and ask the presenter to clarify. In this webinar, we will be introducing Coreform IGA, which is the first commercial native IGA solver, which has leveraged over 15 years of isogeometric analysis research in its development. Coreform IGA is unique among finite element solvers in its ability to calibrate levels of speed and accuracy, leveraging the power of smooth splines and a tight integration with CAD to greatly accelerate simulations while maintaining accuracy. So Coreform IGA was first released in December 2020, and it's being rapidly developed in response to customer input. Like any new software, our feature implementation prioritization is heavily influenced by customer demand. So if what you see today through the introduction, benefits, video demo, or application seems interesting to you, please reach out. We'd love to talk with you and let you either try Coreform IGA today if we feel it's ready for your use case, or learn where you are struggling with traditional FEA so we can enhance Coreform IGA to support you. So I'll start this webinar off with a poll so we can get a little bit more insight into who's on the line, and then I'll turn this over to Greg. So here's the poll. All right. How familiar are you with isogeometric analysis? So if you can just go ahead and vote. So you can say, I know almost nothing. I'm aware of the basic concept. I've read research papers. There's a lot of them. I've done IGA research myself, or I have used IGA software. So go ahead and leave this poll up just for another few seconds. Okay, 3, 2, 1, and run the poll. And here's the results. Let's share them with everyone. So there's kind of a mix of most of those things, but with not many people that have touched IGA software yet. So this will be a great introduction. Okay, so just a little bit about Coreform LLC. So we are the fastest growing simulation company on the Inc. 5000 in 2020. We are centered in Orem, Utah, but since COVID hit, we've gone fully remote and done all of our hiring throughout the US and Europe. So we're excited again to introduce this product to you today, and I'll turn the time over to Greg.
Yeah, thank you, Matt. Yeah, and this picture reminds me that this was the last time that kind of before COVID that Coreform was able to get together, and we've grown quite a bit since then. So we're all eager to be finished with COVID and to have vaccines and to be able to get back together again in person. And I want to thank everyone also who's attending today. I want to thank you for your time and for your attendance. So why Coreform IGA? So many of the people who are on this call may be themselves finite element analysts or might manage folks who are performing finite element analysis. And there is a bit of a landmark study that's been referred to over and over from Sandia National Labs that looked at the workflows of simulation analysis. And they found that from a value added standpoint, there actually wasn't there were a lot of steps like analysis style model creation, editing, so defeaturing of geometry, modifying or healing the geometry, decomposing the geometry to prep it for hexahedral based meshing, the actual process of meshing and iterating on that, and then manipulating the mesh for producing high quality meshes. Those are all things that weren't value added, and they're extremely labor intensive compared to the compute time on a computer, where the computer works 24/7, except for me, maybe it's got some downtime, but 99.9% uptime. Computer doesn't complain. And so it's all this labor that is actually causing a lot of lag in time and in money, in cost and money. The intent or the desire is to drive these non-evaluated parts as close to zero as possible. And to do that through reducing the meshing time. And by doing that, we can radically accelerate product design, as well as analysis. So when there's failure analysis, we need to do a simulation to understand why things failed. We can accelerate that process as well. And we can do this through our proprietary advanced spline basis functions, which increase simulation accuracy and provide us the flexibility we need to decrease the meshing time. Now, if we look at the landscape of mesh technologies and how they relate to simulation performance, we're going to look at the performance of simulation from total time to solution, from slow to fast, but also the accuracy from low to high. Traditional hex-based FEA is slow relative in terms of being able to total time to solution because it's very labor intensive, but provides high accuracy results, which sometimes you have to have for critical, mission critical parts and failure analyses. Temp-based FEA provides a much faster overall time to solution than traditional hex-based FEA, but you sacrifice some accuracy per degree of freedom. And there are additional techniques that are coming out, like traditional meshless methods, voxel-based methods, which provide even faster total times to solution, but sacrifice accuracy even more. With our advanced spline technologies at Coreform, we've actually now increased the accuracy level that can be attained by modifying or augmenting traditional hex-based FEA with body-fitted U-splines, high-order smooth U-splines. And because of their high order and their smoothness, it reduces some of the constraints on the quality of traditional quality of a hex mesh that we might prescribe, as well as less time iterating for the analyst and trying to get the right knobs turned to get accurate solutions. But it's also not it still is not as fast as we could be. And so what we're now looking at with Coreform IGA is the other regime where we can take immersed U-splines, which now provide still high accuracy because they're high order smooth basis functions, but are now much faster than traditional hex-based FEA. And it's this entire regime that is what Coreform IGA is developing a software solution and different technology solutions for. Coreform IGA provides greater accuracy per degree of freedom, as I mentioned, but it's also isogeometric analysis. It has a tight CAD connection. Because of its local additivity properties of our underlying U-spline bases, you have more efficient computes. And then the flexibility that's offered by our proprietary technique allows the analyst to calibrate the speed and accuracy that they need to solve the problem for their customer. And let's talk about how we allow the analyst to calibrate their speed and accuracy. So as I mentioned, we provide now a spectrum from traditional finite element approaches where if the analyst desired or still needed to maybe do some defeaturing, so maybe there are some embossings that still just don't make sense to have featured, you might do some defeaturing, but traditional FEA is attainable with our U-spline technology. But there might have been features in the underlying CAD that made it impossible, or at least impractical, to build a body-fitted hex mesh for. By using a mostly body-fitted, but maybe reducing the requirement of body-fitted in some regions, we can restrict that requirement that allows us now to build a high-quality hex-based mesh with high accuracy per degree of freedom. And if you don't need that level of accuracy, but you still need maybe some general accuracy, you can even defeature quite a bit more. And now our computational domain here shown in purple, now it captures like the outer radius of this piston, and it captures the symmetry faces. But other than that, it's really just, we're going to use our adaptive U-spline technology to drive in accuracy where needed. So we can still get to any level of accuracy that the user needs, but it's just going to cost a little bit more in computation time because we'll need to drive more local adaptivity. And you can go all the way out to a almost no manual labor whatsoever, a fully immersing bounding box, and then completely reliant or using the local additivity of our U-spline technology. Now, I want to show you this in action on an example problem. Actually, before we do that, let me just focus in on that second from the left picture here, just to show here's this geometry with, if you wanted to do a traditional hex-based mesh on this, there are these knuckle fillets or these shoulder fillets here, which make this problem almost impossible to build a hex mesh. It's possibly impossible for an analyst in a reasonable amount of time to build a usable hex mesh on this. But you can see how we've now restricted this requirement, or we've lowered or removed this requirement by this purple computational domain, which immerses these features but still follows the general shape and structure of that volume. But now we can use our U-spline technology to locally adapt and refine where needed to accurately resolve the stresses there. So we've, as an analyst now, I've calibrated that I need to get a solution out to the customer quickly, but I do still need a fair amount of accuracy. And this has allowed the user now to drive that in. Now I want to show this in action. So I'm going to show this example of a ASTM E8 tensile bar. So we can load this into Qubit as a geometry. So a traditional finite element mesh preprocessor that supports CAD operations and meshing. And we can represent this tensile bar as a cylinder that is only body fitted on the grip lengths and then immerses the fillet's reduced length and the gauge length. And using Qubit, we can design our hex mesh as we need to on that cylinder for quality, and we can build a U-spline native into Qubit. That's never been done before, having Qubit natively now supporting spline technologies. We can then create an input file and submit the simulation to our Coreform IGA solver, and then view the results back out in peer review. And so on this slide, we're seeing the U-spline elements that contain at least one quadrature point within the volume. And now we can see we're looking at quadrature points of the stress results and also displacement results. And this is brand new capabilities that we've added in the last few months. And this is progressing at a quick pace. And we'll talk about that later, that Coreform is releasing software now quarterly and actually moving to an even faster release pace as we're developing capabilities. Let's take a little bit of a closer look now at that. So again, just that we have this tensile bar, that if I wanted to build a quality hex mesh on this, I might need to do at least 2 partitions, maybe for my gauge length. I might also need to add another one around the, on the other side of the fillet. But instead, we can just completely approximate this entire tensile bar as a quadratic U-spline cylinder that immerses it. And so it's a tight CAD connection, but we also aren't sacrificing accuracy. And so comparing accuracy per degree of freedom, we can see that with 15 times fewer nodes and 30 times fewer degrees of freedom, we can get stress results that are within 0.1% of leading traditional FEA solvers. And that's just astounding. Next, actually here, I'd like to pause for a bit and see if there are any questions. Because this is maybe a new way of thinking about simulation technology. So I'm sure that there are some questions. So Matt, do we have any?
Yeah, so there are a few questions. So question on the solve time for how long this is taking in Coreform IGA and if that's optimized yet.
Sure. Okay, sure. So one of the things I'll say is that we'll talk about this later, but we use the PETC, the open source PETC solver library. PETC is fully parallel, provides direct solvers, iterative solvers, from like Krylov solvers. And so we have the full power that's in there. If you look at just from degrees of freedom, because we have smaller systems of equations, those should solve faster. We have smaller systems to solve. Additionally, currently with the code that I was using there and demonstrating there, since I was on Windows, I was only able to use the direct solvers on single core, largely because PETC is not yet supported on Windows. However, Coreform is actively working to port PETC over to Windows. Mike or Dr. Scott, do you have any other comments on that?
What I would say is if you look at this example, where you've got what, about 30 times fewer degrees of freedom, then this particular problem will solve much faster in Coreform IGA than I think this was an abacus simulation on the right. However, if you have like the same number of elements, because you're higher order and smooth, each element requires more time to assemble. So it's a trade-off, right? So what we tend to see in practice is that in general, you're going to have at least one order of magnitude fewer degrees of freedom. And so we almost always, our solve times are almost always dramatically faster. But again, that is a problem dependent issue.
Yeah, and one of the things I'll say also is that one of the things that is kind of intangible, but we've noticed that because these problems are smaller and they are very well conditioned because of the smoothness of splines, that they're more robust. And when I say robust, I mean that from my experience using other codes, that you would have problems that would fail to converge at certain points. And then you're going into like the solver settings and trying to find the right parameter value pairs to get yourself through some instability or some issue with your solve. And you spend a lot of time like tweaking and iterating your input text. And we don't really see that currently in our solutions, that typically very, very simple default settings tend to just work. That may start to change a little bit as we start tackling more and more difficult problems, but we have tackled some very difficult problems with some very basic solver settings.
So a couple other questions that have come in. Does Coreform IGA model contacts between parts?
Yes, yep. We support any nonlinearity that you would find in a typical structural mechanics code. Now this code is new and we are adding functionality, but we have demonstrated contact. Dr. Scott can probably talk a little bit more about contact in this partially immersed setting. Might also be useful to talk about boundary condition and position. What do you think, Dr. Scott?
I would say let's just continue. There's a lot of questions coming in, so
Okay.
let's
okay.
I'm handling a lot of them on the chat.
Sure.
And then at the end, we can have a wide open discussion about these, the range of topics.
Good. Great. Yeah. And so as I alluded to, we've done several projects, actually many projects with our early adopters. I'd like to go through at least a couple of those right now. So the first of these is was provided to us from our partner, our collaborator, Kansas City National Security Campus from the Department of Energy. They have an application with flat flex cable delamination. Just to orient you, flat flex cables connect printed circuit boards together. Oftentimes, you might have a bunch of electronics you need to be able to perform a task, but you're constrained by space. And so you split your board into two boards, and then you use a flat flex cable to then connect them. And as you can see here, this cable is now bent at a certain radius. And the question Kansas City had was that they were noticing as they were bending cables to certain radii, that during environmental testing, that these cables would start to wrinkle and then delaminate, which could potentially lead to failure of these cables. And so Kansas City had developed simulation technologies or simulation workflows to analyze these with traditional HFEM style codes. And so on the right here, we see a mesh from a traditional HFEM solver with using many of the rules of thumb that many of you may be familiar with, of making sure you have a minimum number of elements through a thickness. And in this case, the top is going to be in compression. That's where the wrinkling's happening. So there's a finer density of elements at the top. The problem that then Kansas City did, or the equivalent that Kansas City developed with our high order U-splines, is shown on the left. And a couple of things to point out is you can see that because of the higher order, we can exactly capture this geometry with one element. And we can also terminate our elements with T-junctions that are fully supported in the basis. So they're not hanging. There's not a need to do a tied constraint between them. They're fully supported by the U-spline basis. And we're also able to implement mixed continuity, so to have traditional C0 continuity at material interfaces. And on the right is an animation showing this nonlinear analysis running in Coreform IGA. And you can see it's colored here by stresses. And as we notice at the very end of it, we start to see wrinkling. And we were able to give this capability back to Kansas City for them to be able to use to predict wrinkling. And compare it again back to their traditional solutions, that they were using upwards of 10 million elements to get solutions, and we were able to solve this with under 11,000 elements. It's 1,000 times fewer total elements. So as Dr. Scott had alluded to previously, that by drastically reducing the number of elements we have, even if each element is a little bit more expensive than traditional FEA, the almost exponential increase in accuracy per degree of freedom or per element is what allows us to be more performant. Additionally, they were unable to get stable solutions using an implicit time stepping method, and so they had to resort to a mass-scaled explicit dynamics study. We were able to solve this with default implicit dynamics solver settings. We didn't bother to use anything like like automatic time scaling. We just use a set 250 time steps. But even that is 20,000 times fewer total time steps. And in all, this led to almost 1,000 times faster runtime by reducing their computational needs from an entire high-performance computer for about a day and a half down to a laptop in 16 hours. And that's drastic. And that makes this problem tractable for Kansas City. Next, I'd like to talk about an application that's of high importance to Idaho National Laboratories. It's a nuclear fuel rod. And just to orient you here, a nuclear fuel rod is comprised of uranium oxide pellets. Oftentimes, this rod will be like 300 or more pellets long that are then surrounded by a zircaloy cladding. And as they produce energy, they increase in temperature and they expand, as we see in the top right figure, and they begin to press against the zircaloy cladding. And so this is a tough contact problem. Traditional finite elements, you would use many low-order finite elements. And now instead of solving like a cylinder or a circle, we're actually solving like a 30-sided polygon or polyhedron. And it's important here from a pre-processing stage to make sure that your nodes are somewhat lined up between the cladding and the underlying fuel pellet to make sure you don't get poor convergence in contact. On the right, we can see the U-spline solution that Coreform developed. High-order smooth splines allow us to have fewer overall elements, but also exactly capturing the initial geometry of this cladding with smooth contact. And what this leads to, compared to the initial solution from INL's open source Moose finite element library, you can see that the contact pressures should be smooth along the radius, as well as smooth along the length. There should be smooth transitions in contact. And instead, we get these spurious kind of checkerboarded patterns. And that's representative of then the difficulty that we see as FEA analysts in getting contact problems to converge and having to make sure that we got the right solver settings in order to get convergence. Coreform IGA, however, we can see we have smooth contact pressures both along the radius and along the length. And what this was kind of meant for Coreform as we were solving this is that the problem just solved. There wasn't a lot of tweaking that we had to do to get convergence. And contact, for those who maybe aren't as familiar with solid mechanics kind of finite element analyses, contact is one of the most difficult nonlinearities to solve in these workflows. The next example, so I guess those previous examples kind of showed the body-fitted, kind of taking traditional hex-based FEM and augmenting them with high-order smooth splines. And our immersed technologies are relatively new compared to the years of experience we have with traditional hex-based FEA. We aren't able to share any of our partners' problems at this time. So instead, I'm going to show you a demonstration of a complex, partially body-fitted, partially immersed model, just to show and demonstrate the capabilities that we're providing with Coreform IGA. And because of that, I'll mention that since we don't have domain expertise in this area of automotive tire design, that this is not reflective of the actual real life application, but again, rather of a demonstration of the capabilities. Now on this slide, here's a figure or pictures of the model we want to analyze. It's a wheel assembly with a tire and a rim. And as we can see, there's again a gap between the rim and the tire. And then we can see the treads are then cut into this outer range. And on this next slide is the Coreform IGA mesh that we've built that immerses that geometry, but partially body fits in regions. So one of the things we can notice is that if we really cared about, say, our tire, maybe for like contact pressures and friction, or tracking, how much traction do I have on a road, that we are body fitted here. If you were to change, this is where the tight CAD connection comes in. If you were to change the tread design, as long as it stayed within this envelope of this blue region here, you wouldn't have to remesh to analyze a new tire tread design. This one mesh can be reused over and over and over without updating. And here we show the results of this sample problem, showing just von Mises stress. Again, it's a demonstration of capabilities. We're showing the quadrature point results here. And just to show that if we had wanted to, we could do local adaptivity in regions to then resolve regions of high stress. And those are all things that are available with our high order U-spline technology. Now, to compare then with maybe if you wanted to retain the type CAD connection, I found no way in several weeks of looking at this problem, I found no way to simplify this geometry so that I could do a hex-based mesh without drastically changing the model problem. And so me as an analyst, I would resort to a tetrahedral-based solution. And as you can see here, the amount of degrees of freedom that you pay for in order to have a tetrahedral mesh compared to our high order U-spline mesh, that is several orders of magnitude difference there. But we can get you the same extra degree of freedom. And if we actually now look at the cross-section view of this, we can use local adaptivity as needed to refine stresses. But even this 5.5 million element mesh is not refined enough to capture accurately stresses in some regions. And so this is, for both cases, these are a little bit of an underestimate of the amount of elements, but with our high order U-splines and that greater action per degree of freedom, you will have fewer elements and fewer degrees of freedom with our Coreform IGA solver. Next, I'd like to introduce our software products. Two software products that Coreform is currently distributing are Coreform Qubit and Coreform IGA. Now, Coreform Qubit is our advanced meshing simulation tool and model preprocessor. Many of you might be familiar with Sandia Qubit, or there had been a commercial version called CSIMsoft Trellis. Trellis has now been rebranded as Coreform Qubit. And it really ties into the decades of development that have gone on at Sandia National Labs developing Qubit. And we co-developed the Qubit software with Sandia. And we're grateful for their support. Now, Qubit is an unrivaled hex mesher with state-of-the-art structured and unstructured hex meshing capabilities. But it also provides tet meshing or tetrahedral meshing, as well as from hexahedral through pyramid to tet. So hex to tet meshing is also provided in Coreform Qubit. But Coreform Qubit is more than just building a mesh. It also provides the user expert level control of their mesh. And so you can design the mesh as you need to solve your critical problems. We also have standard geometry cleanup tools that are provided from the ASYS geometry kernel that underlies it. And all those things combined give you a comprehensive tool set for everything that you need to do to prepare your models: pre-processing, meshing, and exporting. And then finally, perhaps the most powerful tool of all is that everything in Coreform Qubit can be automated. And we also have a Python API that can subsume all commands in Coreform Qubit and can be exported from external libraries. And so with these tools combined, Coreform Qubit is an extremely powerful tool for your model preprocessing regardless of what simulation software that you use. Here's a video of the show of Coreform Qubit in action producing a U-spline mesh, but also demonstrating that all of the traditional workflow functions that you would expect in a hex or in a finite element mesher are provided. So everything from defeaturing of small features to doing model decomposition are provided. And there's imprinting and merging. So if you need to have a conforming mesh, you can imprint and merge. However, with Coreform IGA, it's not even necessary to have conforming meshes. As I also mentioned, Coreform Qubit provides the user precise control over their mesh, so you can design your mesh exactly as you want. So in this case, maybe we're trying to remove extraordinary points from our eventual U-spline domain. And this is the kind of control that you won't find in a lot of other meshing software, but you'll find in Coreform Qubit. And lastly, as I alluded to, once you have a mesh, we can produce a native U-spline in Coreform Qubit. And it's not just in Coreform Qubit, but we also support exporting U-splines out to, say, the visualization toolkit and ParaView and other simulation codes. And many of our simulation partners are implementing U-spline technologies in their solvers as well. We're also excited to announce that there's a free version of Coreform Qubit called Coreform Qubit Learn. It's available for non-commercial use, and you have access to all of the training materials on our website. It's fully featured with a limitation of exporting up to 50,000 elements, which you should find is more than enough, especially with high-order U-splines to solve relatively complex problems. And you can get your free license by going to our website at www.coreform.com. Next, I'd like to introduce Coreform IGA, especially its feature set, so the things that you care about as an FEA analyst. As I've mentioned before, it is a native implementation of isogeometric analysis, or of IGA. We provide both linear and nonlinear solvers, again, through the PETSI library. We can solve static and dynamic physics. We can use implicit and explicit time integration schemes. We support nonlinear materials, geometry, contact, and more. If you're interested in implementing your own user materials or subroutines, we use Julia as our user subroutine interface and user material interface. And that's a high order language that doesn't require you to worry about pointers and other things. And it can still resolve nearly the same performance as many lower level languages like C++ and Fortran. And then finally, our input files are human readable, currently encoded in the ASCII JSON format. And just to reiterate that why Coreform IGA is that it can help you save money by giving you better simulations through better geometry, allowing you to decrease the burden of model preparation, speed up your solutions, and remove the difficulty or reduce the difficulty of producing convergent solutions. And we're excited to have you all on this webinar, and we'd like to invite you all to join us as we develop the future of FEA. And we'd invite you to go to our website to learn more about Coreform IGA, but also to consider becoming an early adopter of Coreform IGA. We'd love to discuss with you your difficult problems where maybe traditional FEA is falling short or is too burdensome on your organization to continue doing. And we have a partnership program, a strategic R&D partnership program that if you're interested in becoming an early adopter, that you may be interested in. And so we invite you to then contact us to talk about how we can provide a solution for you. All right. Are there any questions?
Great, thank you very much for the webinar. Yeah, there have been a number of questions that have come in. I think we've answered at least an initial response in the back channel with a lot of them. If additional questions remain or follow-on questions from those ones that we've given initial response, please kind of poke us again, and we can talk about any of these in more detail. One question that did come in that we wanted to save for this discussion was if we could do some comparison or go into some details as far as how IGA compares to mesh-free methods, how it may be more accurate, and what those different considerations are.
I can take, there was also a question about, I think, a similar vein, comparing, you know, like smooth functions to low order tetrahedra. And my response to that is, if you look at the literature, it's those comparisons between different element types and FEA technologies are, I would say, scant and kind of not terribly pleasing. And I would say that there's a good reason for that, and that is because those kinds of comparisons are, in our experience, almost completely problem dependent. So we rarely, like when we work with our customers, the approach that we take is, look, if you have a problem where you think you would like to see some improvements either in model preparation time, integration with CAD, simulation accuracy, then we tend to work with our customers on a problem by problem basis. And in our experience so far, in all cases, it has been fairly simple to beat in terms of both simulation solver performance and model prep time, most of the existing workflows and technologies that are used. We actually, in terms of, and so, you know, the comparison between TETs and smooth functions, you know, just broadly speaking, it is the picture that we see again and again with all of our commercial, you know, customers who have large FEA simulation organizations, is what Greg described with that tire, where oftentimes the meshes are massive, but the model building capability is quite advanced with the TET meshers. And what we're showing with our with some of our immerse techniques, or partially body fitted techniques, is that in fact we can build those models faster and with far fewer degrees of freedom. With meshless techniques, we actually use a lot of meshless techniques. As you've noticed, we have a technology where part of your model can be immersed or non-body fitted, and part of it can be you know, body fitted and represent the geometry accurately. And so we view that as an integral part of what we do. And so it has a place. It's a very powerful tool, a lot of those meshless techniques. And so they find expression in a lot of the things that we do.
Thanks, Mike. So another question that's come in, how are U-splines different from NURBS?
Mike or Dr. Scott, do you want to take that one too?
I'd be happy to. So the U-spline technology that we use at Coreform, we developed it primarily because we wanted to be able to achieve a connection to an existing meshing capability like Qubit. And in order to accomplish that, you need to be able to handle unstructured configurations. And in addition to that, we wanted to be able to vary the degree of the elements locally. So you could have some elements that were 1 degree and then another patch of elements that were a different degree. We wanted to be able to vary the smoothness locally. And then we also wanted to be able to have changing mesh resolution, either through the introduction of hanging nodes or interface elements like triangles or pyramids, and so the U-spline technology was constructed in order to meet those internal requirements that our customers had. Where if we didn't provide that level of generality, it just wouldn't have been useful, there would have been no direct connection to any of their existing workflow or modeling paradigms. It's different from NURBS in that you can have, you know, in the FEA world, we use the terms Hpk refinement, where H refers to, you know, like element subdivision, P is changing degree, and K is changing smoothness. In the NURBS setting, you tend to have a fixed degree, and any change, you know, any changes in smoothness or element density, those local changes tend to propagate through a NURBS patch, and so you have a proliferation of degrees of freedom. It's not totally local, and so the U-spline technology, as well as other technologies in the context of overcoming some of these deficiencies in NURBS, seek basically to overcome those global characteristics of the NURBS layout. And so what we've done is we've also incorporated the boundary representation technology, as you saw in the demo that Greg showed with the tensile bar, where in fact you build kind of a very simple U-spline CAD representation, and then you embed the exact B-rep geometry. And so that's an additional generalization that's important to the customers that we work with.
Thanks, Mike.
And if I might, Dr. Scott, so U-splines are kind of in many ways just a generalization of NURBS and B-splines, right? And they, I guess kind of at their core, you can think of them as, right, the user in Qubit is defining a mesh layout and then prescribing, right, so they're prescribing what they want in that mesh. They're prescribing, here's what degrees, like polynomial degrees I want and where I want them. Here's the smoothness that I want. Here's the layout that I want. And then we have a very general approach mathematically to then construct the basis spline, right, through our U-spline technology that then accommodates those requests from the analysts, right? And so that's, in that way, it's really just a generalization of NURBS. But U-splines can also be rational, so they also have that capability as well.
There's a question that we answered back in the chat that maybe we could answer verbally as well. How much of Coreform is based on T-Splines? So T-Splines was actually my former company that we sold to Autodesk maybe 10 years ago. T-Splines are also an unstructured spline definition, and there's was one of the original kind of inspirations about how to push isogeometric analysis beyond NURBS into more of an unstructured general format. U-splines are a generalization of all of those technologies, and actually we've worked with Autodesk so that there's a way to export T-spline models in Fusion 360 that can be then used for simulation in Coreform IGA. But U-splines, like Mike was mentioning, is a more general technology that's been specifically developed to support simulation. And so there's a volumetric extension, you can have varying degrees and so forth. Okay, let's see some other questions that have come in. Okay, here's a question, sticking on the spline-based questions from Stefan. Is it easy to transform from NURBS patches to U-splines?
I can answer that, Matt.
Yeah.
Yeah, so it's fully NURBS compatible in the spirit of T-splines, meaning that you can extract a lossless or an exact NURBS layout from any U-spline, just like the T-spline technology. And in fact, we export to step. We have that technology today, where you can build a U-spline, and we have some customers that are also using the technology just for projects that involve common kind of CAD workflows that don't have anything to do with simulation. So they're primarily interested in surfaces, and so we have built out capabilities that allow them to export directly to step in a lossless fashion that they can then read into other tools.
Some other questions. How are assemblies?
And for those who aren't,
Go ahead, Greg.
was just gonna say, and for those who aren't familiar, STEP is a neutral CAD format that's commonly used in industry to pass geometry between CAD softwares in a vendor neutral manner, and it's an ISO standard. Sorry, go ahead, Matt.
Yeah. Another question, how are assemblies modeled or represented?
So, you know, a lot of our most impressive results are currently proprietary, which is almost all of them are assemblies. And so the way that assemblies are handled is we use a lot of existing FEA technology. For example, connections between different parts, especially for automotive customers, is a big deal. And so we actually have a very active project right now where we are translating a number of important advanced connection types over from what you would find in a traditional FEA kind of assembly structural setup workflow over to Coreform IGA. And so we tend to take two approaches. We often reproduce exactly the FEA technology, but in the context of a U-spline basis. That's what we tend to do first. And then we often will generalize or improve upon those connection types and make them kind of native to the environment of U-splines and the immersed technologies that we use. So yeah, so in terms of Coreform Qubit and U-splines and building models, you can build very, very complicated assemblies of parts. Generally speaking, the limitation, the current limitation in IGA technology in general is there are, when you get into kind of industrial scale problems, connections are a big deal, and they tend to be very industry specific. And so that will be, you know, building out a full suite of connection technology will be something I'm sure we'll be working on for years to come.
Yep. Yep. Yeah. And Dr. Scott, you reminded me that there was a question that we tabled earlier that was dealing with contact. And maybe contact is also an interaction, and so maybe it's a good time to revisit that question. How do we handle contact within Coreform IGA?
So we support both. We support the spectrum where you can have contact between body fitted contact surfaces as well as you know, immersed and any mix in between. We have very sophisticated collision detection algorithms that leverage the kind of the fact that we're using splines, and we have a kind of a single surface algorithm that a lot of our customers, our automotive customers, are working with us on. The underlying formulations that we support, you know, generally speaking, we start from kind of an augmented Lagrangian framework and then derive a series of methods depending on what the customer wants, whether it's a pure penalty, Nietzsche type method, whether it's, you know, some mixed or splitting scheme that they want to use. But our general framework for constraint enforcement always kind of starts from the augmented Lagrangian point of view and then specializes from there. And the same thing with the contact.
So here's a question from Pablo. I understand Coreform is especially useful and fit for simulating when my geometries are in the CAD format like IGES. If for a particular application, my geometries are only in a mesh format like STL or STEP, would Coreform be able to process and simulate with them, or would that not make sense at all?
Yeah, so that's a great question. And in fact, one of the reasons that we have this, we call it the method that we're using, we call internally the flex method, the flex representation method, where you have kind of a method that allows you to be immersed or body fitted or any combination in between, and it's one formulation. So what that allows us to do is to integrate CAD representations that are way beyond just the standard mechanical CAD formats like VREPs. So the minimum amount of information that your quote unquote CAD representation has to provide is whether a point is inside or outside the model. So it can be an STL file. It can be like a mesh or faceted format. It can be traditional BREP CAD. We have a project, a very exciting project right now where we're integrating a new CAD kernel based on implicit modeling into our capabilities so that we can work with a lot of the emerging CAD capabilities that are being developed for additive and generative modeling that are going beyond kind of the parametric surface representation. And for us, we don't have to change anything in our solver technology. All of those CAD formats we designed the system in order to be able to accommodate them directly.
Great, thanks. Okay, a question from Luis. Is it possible to do heat transfer? I'm thinking in solidification problems.
So we have done some, what I would say, loosely coupled heat transfer problems. In other words, we don't have a fully kind of coupled solid heat transfer capability. We do some kind of what I would call static heating. That is something, however, that I think is right around the corner. We have customers that are asking for some multi-physics extensions to our capability. I would imagine that heat transfer will be the first that we implement.
Yeah, and that's a good point that you mentioned also, is that we are developing solutions for customers who have problems that we can't solve. And so many of the capabilities that we currently support, we can directly tie them back to a specific customer problem. And that's where, if we're actively interested in solving tough problems that you may have, and we're completely reliant on our customers and our early adopters to help drive what the simulation needs are that we need to implement. And so
yeah, we never implement features without a customer request.
Right.
How clean does my geometry have to be to get accurate results, and what level of accuracy can one expect on the surface of the immersed section of the model? So this is an area of a little bit of exploration for us. We're finding that we can accommodate extremely dirty CAD geometry. Again, you need an inside-outside test, and so there are certain scenarios where you may lose a quadrature point here or there, depending on how bad the geometry is, but that ends up being, from a practical point of view, a non-issue, at least for the problems that we've solved so far. And so one of the things that's very important to our customers is they do not want to do CAD cleanup, and so we often get CAD where you can't get a mesh on it at all, and we will still be able to generate nice results. I think the follow-on was the stress.
I would like to clarify one thing, though, Dr. Scott, that there is, the geometry can be dirty, but it needs to be correct, in that if you have things that you meant to be connected, but they are, say that they are feet apart from each other, and the model tolerance that you're using says that things that are more than an inch apart are disconnected, we respect that. And so that no simulation tool can get you around incorrect or not, non-physical geometries that you've modeled. So that is the thing. But what we've done is now, like, the dirty, where you've got like small gaps in your geometry that kind of plague traditional finite element solvers. That's what now we've got. This flex model is now very robust too. So I do want to make that one clarification. But those, oftentimes, like those issues with, like, I've got these pieces that are way too far apart, there are tools in Qubit that can then fix those problems fairly easily. But I do want to just make that one clarification. Sorry, and I'll let you continue, Dr. Scott.
Are there more questions still? Looks like there's a few.
Yeah, there's a few more that come in. So Do we have plans to enable topology optimization capabilities?
We actually have a project right now that's working in this area. One of the really exciting things about this flex capability is that really the only model you need, the simulation model you need to build is what we would call the design envelope. And then within the design envelope, you can employ an optimizer like a topology optimizer to explore a whole range of designs without ever having to mesh for validation studies with simulation. And so, yeah, so this is a very obvious extension. There's a lot of interest from a lot of our customers. So we actually are developing a capability right now to solve that problem.
All right. Is staggered solution algorithm included in Coreform?
Again, we don't have a full-fledged multi-physics capability yet. And so that would be, we would probably, again, once we have customers who are pushing for, you know, heat transfer, fluids and fluid structure interaction, I think that would be when we would explore some of those staggered schemes. Generally speaking, we solve for all of our degrees of freedom in a monolithic fashion.
Okay. Question from David in the chat window. How do you suggest forming an IGA structural model based on a point cloud of geometry based on a measurement of a part from something like LiDAR? What would the workflow in the context of Qubit or Coreform be?
Yeah, so that's of interest to us for obvious reasons. I mean, it's one of those extensions where there's a lot of point cloud data and not a real clean way to build models. So for a point cloud, what we need again is to be able to answer the kind of general question, is a point quote unquote inside or outside? And so there are techniques with point clouds where that can be answered. You will still need to be able to build triangulations over certain parts of the point cloud, but just for imposition of boundary conditions or contact. And that triangulation does not need to be clean. It just needs to be something that we can form integrals over, but we wouldn't need to build a basis over it, for example, for most of the kinds of things that we would do. And so this is of interest to our DoD partners, where for them, they are often working on repairs where they have scanned data and they want to understand like the as-built or the current state of a particular part for repair. And so they're very interested in doing that kind of simulation. And so these tools enable that kind of extension of the concept of CAD.
I just know at the time we're coming up on 11 o'clock Mountain, so recognize the number of you will have other meetings or engagements that you'll need to move on to. There's still a couple of questions left that we'll stay around for a few more minutes to answer. But I just want to take the time to say thanks to everyone for the time that you took to attend the webinar, and we look forward to continue to engage with each of you. So these are the questions that
we will be posting the webinar on, we will be posting the webinar on YouTube afterwards. So if you do have to leave early, if you wanted to catch the last few questions, you can do that later.
Great, thanks, Greg. Okay, so here's another question. What does dynamic physics mean in the slides? Solidification problems or Cahn-Hilliard problems?
Greg, I think you meant just time dependency, right?
Yeah. So oftentimes you'll want to solve like a static or a quasi-static problem. So yeah, I'm talking mostly in our current capabilities being solid mechanics. That some of our customers have problems that are statics, and we can solve those. But also we have other customers who care about maybe say like crash physics, things that happen on very small timescales. And so those are maybe more dynamic. And so we were able to solve those dynamic problems as well. That's more of what that slide meant.
Great. Have we tried IGA for explicit dynamics problems? What is the current number for IGA versus FEA in this case?
Yeah, so explicit dynamics is something that is is we have a number of large automotive companies that we work with, and the physics that govern a lot of the kinds of problems we're doing there are almost exclusively explicit. And there's kind of two answers to the question. So the time step, or the critical time step, is almost always much larger for one of our models for two reasons. The first reason is our element size is often much, much larger. We have much coarser meshes for a given degree of freedom. So that's the first part. We also leverage the U-spline technology in order to, we have techniques now where we can leverage the U-spline technology in order to optimize the spectral the spectrum of that's produced by the basis. And so what we've been able to achieve, which I believe might be the first time this has been achieved, is that we, for a given polynomial degree, let's say for a given polynomial degree, let's say the critical time step was for a linear basis was 1. Generally what happens as you increase degree, that time step will get smaller and smaller as the degree goes up. And that's one of the reasons why these higher order traditional FEA with higher order functions isn't very popular, is that the spectrum starts to be polluted by a lot of spurious noise that is non-physical. With the smooth functions and kind of the local adaptivity property of U-splines, we can actually tailor the basis so that essentially the critical time step stays constant for a given degree and smoothness level K. And so what that means is, so what you'll see is like for linears, maybe the time step will be 1. And then for quadratics, it might drop a little. It might go to like the time step size will get a little bigger, maybe like 1.3 or something, right? And then it'll stay at about 1.3 for all other polynomial degrees. And so what that means is even if the element sizes are the same between a traditional FEA mesh and like a Coreform IGA mesh, we will still have a larger critical time step. And then if you layer on top of that, the fact that the elements are usually much, much larger, we tend to have about an order of magnitude difference between the critical time step for, you know, a traditional linear explicit dynamic simulation and a simulation that we build using our technology. And so for automotive customers, this is a really big deal because if you, I mean, that time step really is the limiting factor for them in terms of how many design cycles they can go through that include analysis for a given, for example, car design. And so if you know their explicit simulation runs are now half as long or a tenth as long, all of a sudden that's a huge win for them.
So here's our final question. Does the IGA solver work on GPUs?
So we have not done any work ourselves on GPUs. We are in connection with the PET-C folks, and we're monitoring some of the work coming out of the labs, where some of the linear algebra packages that we use, those groups are extending those to GPUs for use within the DoD and the DOE. And so our plan is to leverage that capability, but not build it ourselves. And as of yet, we haven't had any need for it, but I'm sure there'll be pressure from somewhere to do something like that in the near future.
Okay, great. Well, thanks again, everyone, for taking the time for the webinar. And it's good to engage with you. We hope this is the start of more conversations and engagement. And we're excited to welcome you to the Coreform IGA community. And we hope you have a great rest of your day.